Hello, welcome to R for Psychology. I'm Dr. Andy Hales at the University of Mississippi, and in this video we're going to look at how to calculate power for t-tests in R. So we're going to be working mostly in base R today. We'll load some packages later. We'll worry about that when we get to it, but for now we're going to use the power.t-test function for all three different types of t-test. And let's start with the most common, the independent samples t-test, for when we have two different groups we want to compare to each other. Now, computing power in R is not so complicated. It's actually really straightforward. So I'm going to illustrate the logic of this for you here, and then you'll be able to apply all sorts of infinite variations for it to answer whatever particular questions you happen to have. So for starters, we can tell the type of t-test we're doing is a two-sample t-test that corresponds to an independent samples t-test. And then these next two pieces of information, they matter, but they're also kind of boilerplate. So you could change these, and the day will come when you'll want to change these, so you need to know about them, but they're not really where the action is. So for starters, we set the significance level. Here it's 0.05. It could be other values, but we'll stick with that default. And you also want to specify what the alternative hypothesis is. In other words, is this a two-tailed test or a one-tailed test? Again, we'll start out with the default two-tailed test. Okay, so for power analysis, the way power works is that once you've fixed the alpha level and whether it's one or two-tailed, there are three pieces of information, and if you know two of them, you can calculate the third. So where all the action is down here with the effect size, Cohen's d, with the sample size, n, and with the power level, the probability of a significant result under those reasonable assumptions. And so again, holding alpha level and the tails constant, if we know any two of these, we can always calculate the third. And that's what we're going to be doing here. There's different situations where you'd want to calculate one versus the others, but the math and the computation, very easy in R. So let's start with sort of the classic power analysis situation where you have some hunch about what the effect size in the population might be, and you want to know how many people do I have to run to have a high probability of detecting some effect size. So let's say I have reason to believe that in the population, the effect size is a Cohen's d of, let's say, 0.45. And let's say that I really don't want to waste my time on a study that's not going to work. So I'm going to calculate the sample size that I need to have 95% power. In other words, I want a 95% probability of getting significant results, assuming that the effect size really is 0.45. Now that I've entered those two pieces of information, n I'm going to leave as null because I'm calculating n here. And the way this works in R is I give it two pieces of information and it returns to me the third. So let's go ahead and run this and see what sample size we would need to have 95% power to detect an effect size of 0.45. So when I run this, most of the information we get below is a repeat of what we told it above. The difference, though, is that we entered n as null because we wanted to calculate it, but then down here in the output, n is now provided to us. N is 129.31. Now, a couple of absolutely critical things to notice here. First, it's even in all caps. That's appropriate. Note, n is the number in each group. This is a two-group t-test, so we're comparing two groups to each other. We need 129.31 people in each of those two groups. So you can do a little math. That's 260 people total that we would need, approximately. Now, the other thing to notice is that we're psychologists. We study people, usually. Good luck running a study with 129.31 humans. Humans don't come in units of 0.31, so you need to round up to the nearest integer. For that matter, if you're running a study and you expect some attrition. You might have to exclude people who were inattentive and failed an attention check. You're going to have some missing data. You want to plan for all of that. So this is mathematically the number of observations you'd have to have in hand to achieve this level of power. But of course, the practicality of running experiments means that it might be wise to even run a little bit more than that. Okay, so in this case, we have learned the sample size we'd need under these assumptions. But there's other ways to go about doing a power analysis. So, for example, we might be curious. In this case, we wanted to know what sample size do I need to achieve a certain level of power, assuming an effect size. Let's switch things up and let's imagine, as is often the case, that we're only able to run so many people. We have limited resources, or maybe we only have so much time to run the study. Well, in that case, let's just imagine that the reality of the universe is that I'm only able to run, let's say, 200 people. Now, if you're paying attention here, you'll know why I just typed in 100 into this box if my goal is to run 200 total people. And if I'm running 200 total people, let's say I want to have, I want to know what effect size I'm able to detect with 80% probability. So it's not up to me what the effect size in the universe is or how big my sample is, but I do want to know ahead of time before I invest the time and energy into running a study. Would the effect size have to be gigantic for me to detect it? If so, then maybe I'm better off not spending my time on this. On the other hand, if this sample size is sufficient to allow me to detect pretty reasonable effect sizes, then that's a good sign that I should go ahead with the study. So here, let's assume we can run 200 total people, and we want to know what effect size do I have an 80% chance of detecting. If we run that, we can see that the delta, the Cohen's d effect size here, is 0.39 or 0.4 after rounding. So now that I know that that's what the effect size is, depending on what I'm studying, I can make an informed judgment. Do I think the thing I'm studying is really that large? If not, then maybe I should rethink my approach. So to round things off here, we could also use an effect size and a sample size to calculate power. So if we set power to null and we provide values for d and for n, we can calculate the expected probability of a significant result. So imagine hypothetically I ran a study and I'm interested in replicating it. So maybe in the study I just ran, I observed an effect size of, I don't know, let's say 0.28 is the Cohen's d I observed. And let's say in my replication study, I want to know, let's just imagine I had run 200 people in the original study, and I want to know if I run that again, what is the probability of a significant result? So under those assumptions, if we run that, we can see that power is not so good. It's just 50%. That's a coin flip. So even if there really is an effect of Cohen's d of 0.28, if I only run 100 people, it's not particularly reassuring that I'm going to walk away with a significant result. So I should probably rethink my design in this case. Anyhow, I hope you can see that by inputting any two of these, we can calculate the third. That's the logic of this. And of course, to reiterate, where we set our alpha level and whether we're doing a one or a two-tailed test, those values also matter, and you should give some thought to them. So just to illustrate in this particular case, if we were really worried about false positives, well, we could change our alpha level. Instead of 0.05, let's use an alpha level of 0.01, and that's going to take our power from bad to abysmal. When we run that, instead of a 50% chance of a significant result, now it's only a 27% chance of a significant result. So then we might consider running a larger sample size, and if we wanted to do that, we now have the tools to see how that would affect power. So that is for independent samples t-test. For the other types of t-tests, it's highly similar. For a one-sample t-test, where you're comparing the mean of your sample to some known population mean or some important value, everything's the same except you change type from one sample to two sample. And just like before, you can input any two of these values and it'll calculate the third. Now, things get a little more complicated with a paired samples t-test, and the reason for that is with a paired samples t-test, the reason it's so powerful, literally it has higher power, is because we can use information from participant scores on one variable, and that helps us predict the other variable. So the more correlated the two variables are, then the more powerful this test is. Now, using this base R function, there's no easy way to input the degree of correlation between the two variables. So instead, we're going to use this function, powers.t.toMeans, from the powers package. And I'm using a little wonky formatting here. The reasons for this are kind of boring, but install the package the way you normally would, and then enter the name of the package, followed by these two colon signs to tell it use this function from this package, and then we can supply it the information we want to calculate power for a paired samples t-test. For starters, we got to tell it it's paired samples t-test, so paired equals true. And then things are familiar. You know what an alpha level is. Alternative uses slightly different syntax. So here we're doing a two-tailed test, so we set it to not equal. If you wanted to learn the syntax for a directional test, you can just pull up the help menu for this function. It'll provide that. And then down here, instead of a single effect size value, we have to estimate our postulated population values for the mean of each condition and the standard deviation of each condition. And importantly, the reason we're doing it this way is we can also enter the expected correlation between the two conditions. And then here we can enter power to calculate the sample size, or we could enter the sample size to calculate power. So in this case, I've told it what I expect the means for each condition are, and I've kept things simple with standard deviation set to 1. And if we run this, we can calculate the sample size we need to have 95% power under these assumptions about the population. And in this case, it's telling us that we need a sample size of 75. Now, this is slightly counterintuitive because it's a paired samples t-test, so that's actually 75 pairs. So that would mean we'd need 75 people, each of whom we collect 2 observations from. Okay, now I mentioned the reason we're doing that is because the degree of correlation between those two measures, it affects how powerful the paired samples t-test is. So imagine that we're running the same study, except we think that these two scores, say it's a pre-post design, if we think that the score on the second measure is really, really highly correlated with the score on the first measure, we could imagine that the correlation is not 0.3, but instead it's 0.6. And if that's the case, it's going to increase our power. And if power goes up, that means we could have the same probability of detecting an effect with even fewer people, which would be really good news for running our study. So let's calculate now the number of people we would need to have 95% power if our correlation is even bigger. All right, now we only need 44. Looking good. So if you're willing to make some predictions about the means and standard deviations of the groups, or at least entertain some assumptions about those values, well, then this gives you everything you need to calculate power or sample size for a paired samples t-test. Cool. That's most of what you need to know. There is one extra topic that is worth being aware of, and it relates to what we started with. An independent samples t-test is when you have two groups and you want to compare them to each other. Now, often, these two groups are the same size, like if you're doing an experiment and you randomly assign people with 50-50 probability of being in each group. But they're not always the same size. Sometimes you're studying, say, gender differences between men and women, and maybe in your sample, it's 60% men and 40% women. Well, now your two groups aren't exactly the same size, and that can hurt your power. And if you want to run your power analysis in a way that accounts for that, there's this function from the power package that makes that very easy to do. So we can load that package, and then we use this function from that package. Again, we should specify the alpha level and whether it's one or two-tailed. And here the difference is that we can enter the n for group 1 and the n for group 2, and they don't have to be the same. That's in contrast to above when we're using base R. They do have to be the same. So down here, instead of like the 40-60 split I just mentioned, let's go crazy here since we've got this function and we're showing it off. Let's imagine a case where it's really unbalanced. Maybe I'm comparing left-handed people to right-handed people, and I'm going to have a lot more right-handed people in my sample. So imagine I have 10 lefties and 90 righties, and this is the effect size I expect in the population. Well, I can calculate my power to detect that effect. And in this case, I can see my power is pretty bad with just 32%. Now, if my sample sizes were more equal, maybe I go out and I post flyers all over town to get every left-handed person I can find, and I get it up to 20 left-handed people and 90 right-handed people. Well, wow, that made a bigger difference than I expect. We went from 30% to 50%. Still not great, still not something I would be comfortable proceeding with, but at least we're getting in the right direction there. We could look at maybe pre-registering a one-tailed test, and that can help. We should also be open to the possibility that the study, we might not have the resources to run, or maybe we need to team up with people and find a way to share resources, run it together, something like that. In any case, that's how you compute power for different t-test designs in R. So good luck and happy power computing.